Hello everybody, welcome to Statistics and Theory. In this video I'm going to demonstrate how to do a multiple indicators, multiple causes analysis within the framework of structural equation modeling. And this is the model that I'm going to fit into the data. For your information, the data comes from this paper which we published in 2019 in this journal called Papers in Language Testing and Assessment. In the paper we compared mimic with Roche-based differential item functioning. In this analysis I just focus on the mimic results. If you're interested to read the paper, I will leave the link to the paper in the comments section just below this video. In addition, I would like to suggest that you can take a look at this book, particularly this chapter, Structural Equation Modeling in Language Assessment, in which we have discussed some of the basic concepts of structural equation modeling. The book is called Quantitative Data Analysis for Language Assessment. This is the second volume of the book. So back to our model here. As you see, we've got 5 test items which are measuring reading comprehension, and these test items are polytomous. They come from the PET test, which stands for Pearson English Test. And here is how these items look like. As you see, they're polytomous. They've got minimum and maximum scores between 1, 2, all the way to around 6 or 7. In addition, I have age and gender. So they have these two variables have been represented in this part of the model. I would like to show you how to develop this model first in AMOS, and following that I will provide you with some of the terminologies that are commonly used in mimic analysis, and then I will show how to fit the model and get the results. First of all, let me open a new interface. In this new interface, since I have only 5 items, I click on this button here and I start creating my model. First of all, I would like to draw a latent rate, which is represented by an oval shape, as I have discussed in previous videos on structural equation modeling and confirmatory factor analysis. Then I keep clicking 5 times because I want to represent 5 items. So 1, 2, 3, 4, 5. This is one part of the model, and I would like to rotate it around like this. So before starting to fit the previous model which you saw, it's important to first fit this basic model. In this form, as I have discussed in previous videos, this is called a confirmatory factor analysis model, or CFA for short, in which we have got one latent factor, or sometimes 2 or more, each of them indicated by or measured or measuring several test items. At least 3 test items are necessary. In some literature you might find 2 items as well. Personally, I prefer to have 3 items at least, so that the error of measurement will not be very high. In this context, I only have 5 items. I have a latent variable or latent factor, and using these 5 items I want to measure this latent factor. Now I'm going to shift back to my mimic model that I had drawn previously, because I think I prefer that to this one. So I don't want it to save changes, and here we go. In this model I have also included gender and age. For the time being, I'm going to remove these 2 factors and just also remove this disturbance or error, and show you how to continue with this model. First of all, I need to connect the model with the data set. So I'm going to click on this and find my data set, which is on the desktop, and click data, click OK. Now that I have linked the model with the data set, I need to click on this list of variables, and very easily I can drag and drop the items into the indicators. I've already done that, as you can see. So I have the 5 items here. If I want to continue the analysis later, after this confirmatory factor analysis, I will then include gender and age following this test. Okay, let me close this. A reminder is that one of these beta or regression weights, which are represented by the one-headed arrows that are running from reading to items, should be fixed or should be set to 1. It's already done. It's already been done by AMOS automatically. But if you do not see that little 1 beside any of these arrows that run from the main latent variable to your items, you should put your cursor on the arrow and double click so you can get to see the regression weight, and just put a 1 there if you cannot see it, and close the window. Next is, of course, we also need to name the latent variables. One of them is reading. In the first model which you saw, there was no reading, so you double click on the oval shape and include under the text, include the name that you would like to have. So here I've called it reading. You can call it anything else, for example, reading test or reading ability, really. And for these errors that are associated with indicators or observed variables, you can also do the same thing, or you just simply go to plugins and click on name unobserved variables. They will be named automatically by AMOS. That makes everything easier. The next step in running this analysis is to go to the analysis properties option and click on the first tab. Under the first tab, I suggest that you keep maximum likelihood method of estimation. This is because my data is normally distributed. So if you also have normal distributed data, that's what I suggest. If you have some missing data in your data set, it's important that you click on this estimate means and intercepts, otherwise the analysis will not be carried out. Next, I suggest that you go to output and click on standardized estimates and squared multiple correlations. You can also get modification indices. Of course, modification indices will be outputted if you do not have any missing data. If you are also interested, you can click on normality and outliers. For this analysis, I'm not interested in that because I've done that before. You can watch my previous videos on confirmatory factor analysis and also structural equation modeling. I'll leave the links in the comments section below the video as well. So let me close this. And now the analysis is ready to run. You can click on calculate estimates. Okay, then all the estimates are calculated. So I think we can either look at these statistics or go to the actual output from this view text option, which I think is something that I would prefer. So I click on it, and the first thing I would like to check is model fit, because model fit is important, because if the model doesn't fit well, then we have to make some modification to it before we start to make sense of the beta regressions, etc., beta values or regression weights, etc. So as you recall from the previous videos, first of all, we can look at the normed chi-squared value, which ideally should be below 3, which this statistic meets that criterion. And as a result, this is the first statistic that provides evidence that our model fits the data well. We also have a p-value which is smaller than 0.01, which is another indication that the model fits the data pretty well. But as I've mentioned before, the p-value often is significant, and this is the p-value for the chi-square test here. So when it's significant, it's an indication that there is a discrepancy, a significant discrepancy between your model and the data. However, the caveat or the shortcoming is that this p statistic is pretty sensitive to the sample size, and as a result, the normed chi-square is preferred over the chi-square and is p-valued. The next thing we can look at is to look at the CFI and the TLI statistics. You can look at some papers. You can look at our paper or book chapter as well. But most often, authors refer to, as a rule of thumb, refer to a criterion like 0.9 or 0.95, and above that, as acceptable and indicating good fit of the model to the data, in these cases, you see that in both of these cases, the data seems to be a good fit because the CFI is 0.986 and TLI is 0.972. Therefore, we have some good reason why our data is fitting well. There are other fit statistics that basically you can look at, and please take a look at our confirmatory factor analysis video in which I've discussed that more extensively. So next we can look at the estimates or beta values or regression coefficients. It goes by different names. The first thing that's important for us is to make sure that there is a significant p-value for each of the indicators or for regression path. And as you see, there is that criteria, the criteria is being met here. As a result, we can say that the test items from 1 to 5 contribute to the measurement of the latent factor reading test. Now, if you want to make sense of the amount of contribution that they're making to the measurement of the latent factor, it's a good idea to look at standardized regression weights. Standardized regression weights are analogous to effect size. So, for example, for the first variable, as you can read from here, when reading test goes up by 1 standard deviation, item 1 goes up by 0.5, 0.06 standard deviations. This is somehow a medium effect size, I would say. If it's larger than 0.7, you can say that it's a large effect size. The largest effect size that we can observe here, which is actually pretty close to becoming a large effect size, is 0.692, which is interpreted as when reading test goes up by 1 standard deviation, item 3 goes up by 0.692 standard deviations. So everything seems to be fine on this in this model. Okay, at this point we can go back to our model and start doing the mimic analysis, since we have evidence that our CFA model is fitting our data pretty well. The first thing I would like to test here is the effect of age on reading test latent variable. So it's pretty easy to do so. What you can do is just to drag and drop your variable, age in this case, into the analysis. Next is, because age is going to be an external or an exogenous variable which predicts reading test. Reading test is becoming an endogenous variable, and as a result we need to have an error term or a disturbance attached to it. So clicking on this button would do the trick. It's a unique variable, in other words. So I add a disturbance or uniqueness variable to it. It's a bit too large in size, so maybe I adjust the size of it using this button. And I'll go back to plugins, name unobserved variables, and the unobserved variable will be automatically named. Next, I want to draw an error from age to reading test, indicating that age has an effect on the reading test variable, and we want to measure how much that effect will be. That's pretty much all of it. So I'm going to click on calculate estimates to see if the new model fits well, and if so, what's the effect of age. So first of all, this normed chi-squared value is slightly above 3. It's not the best model, but I wouldn't get worried about that because my CFI and TLI are not too bad. The next thing I would like to take a look at is the estimates. And as you see, there is some significant impact from age to reading test. And the AMOS interpretation reads like this: the probability of getting a critical ratio as large as 2.32 in absolute value is 0.019. So this is significant, at a p-value smaller than at an alpha level of 0.05. So now we know that age can predict the reading test scores, but how much is that prediction? We go to standardized regression weights to identify the magnitude of that prediction. As you can see here, it's around 1% of, or not 1%, sorry, about 9%, or pretty much close to 10% of the amount of reading test variation, which can be explained by the age of test takers. In AMOS terminologies, when age goes up by 1 standard deviation, reading test goes up by 0.098 or 0.1 to just round it up, standard deviations, which is low, but still in a sense is significant in the sense that we know that age can predict the reading score. Now, I'm not very surprised to see this. Why? Because it might be that as people mature and grow older, they have more experiences in their life, they have probably read more texts, and everything else equal, they would probably have a higher chance to score higher on any reading test. So this is one part of my mimic model. Now some terminologies here. Let me draw some boxes here for you to identify different parts of this mimic model. I have two parts in my mimic model. One part is this. This goes by causal or formative model. It's causal in the sense that variables, or formative, the variable age, causes reading test or forms reading test, and that's indicated by the direction of the arrow. If you want to put it in a different way, you could say that causality here flows from this indicator, age, to the latent variable. Now there's another section to this mimic model which actually overlaps with this, and that includes again the latent variable itself and its indicators. So this part is called a reflective model or an effect model. So you've got a cause model and an effect model. The effect model, on the other hand, shows that the latent factor causes items or variations in the items, to be more specific. So any sort of variance that you can observe and measure in these items, that's in the performance of the test takers, are attributed to reading test on the one hand, and some of it, which is not explained, is the error of measurement, which you can see that has been represented by these circles or E's. So I'm going to go back to this analysis. And what I would like to do at this point is to replace age with gender. I'm going to move in gender. Now I would like to show you how to do a differential item functioning for this test within the framework of mimic. Now I have made 1 or 2 videos about differential item functioning, and it refers to a condition in which people of the same ability level but of different backgrounds, for example of gender, have different probabilities of answering the test item correctly. Within a mimic framework, we need to do 2 things. One is to draw an arrow from gender, which by the way has been coded as 0 and 1, and that's very important for us to remember. See, gender is 0 and 1, 0 for females, and 1 for males. If you scroll further down, I think you can find males. Yeah, these are males. So 0 and 1. So in a sense, this is a dummy variable in which 0 indicates females and 1 males. So male is the main group here, and female is a secondary group. That's a nominal variable, by the way. So what we need to do is to test the affected gender on 1 item at a time. So we need to draw 1 arrow from gender to item 1, and that's going to be our first mimic differential item functioning for item 1, and we have to run this analysis first. After running it, you need to go to the output and of course take a look at the model fit. The model fits pretty fine, as you see by the CFI, which is far larger than 0.9. It's 0.985, and the TLI of 0.973 both indicate a good model fit. In the same way, the normed chi-squared value of 2.232 also indicates a good fit. Now, the most important part here, after making sure that the model fits well, is the estimate. Here, gender neither affects the reading test nor affects nor affects item 1, as indicated by the p-values which are larger than 0.05. This indicates that there's probably no differential item functioning for this analysis, but within the framework of mimic. Remember that when we did the analysis in this paper, we compared Rush-based diff with mimic, where the results were pretty similar, I should say. However, we found that Rush model was able to identify another type of differential item functioning, which is known as non-uniform diff. Okay, back to the model. The next thing we should do is to move the arrow. You can just use the truck icon and shift the location of the arrow from item 1 to item 2, and then run the analysis again. The same process should be repeated 5 times, and every time we run one analysis, we should look at the fit statistics and make sure that the fit is still maintained, which is the case here, and look at the estimates. And as just pretty much like item 1, as we saw before, there is no significant impact from gender on item 2 as well, neither on reading test when the differential item functioning on item 2 is being investigated. So this is good news for the test so far. Next, let's test that for item 3 quickly. So I'm not going to explain in details, just model fit. Yes, it fits well. Estimates, no, there's no significant p-value, therefore there's no effect of gender on item 3. Next, I'm going to change the model a little bit and move the arrow to item 4 and run the analysis once again. Model fit, yes, there's good fit here as indicated by those statistics. Then estimates. Well, the estimates are fine to me too, because it indicates that, again, there is no effect for gender on item 4. But how about item 5? The last one. So item 5, and I'm going to run the analysis and click on the estimates. The model fit is pretty good, actually much better than the previous ones, as you can see indicated by the normed chi-squared value. I'm going back to the estimates, and we still see that there's almost, well, this is getting close to 0.5, but still it's non-significant. Even if it were significant, with a very small effect size here, I would say that it wouldn't really count that much as a significant observation here or anything of concern in the validity of this test. So that's pretty much all about it. One last thing is that we can also include both gender, let me remove this, and age in the analysis. So let's click on this variable list and bring in age, close this again, and draw an arrow from age to reading test and run the analysis. Once again, we are prompted if we want to correlate gender and age. I'm not sure if I want to do that because I don't have any theoretically justifiable reason for correlating these two variables in the first place. So just proceed with the analysis. And of course, this immediately shows that there is no effect from gender on reading, but let's just confirm. Model fit, it fits fine. Yes, it fits good based on the TLI and CFI and the normed chi-squared value. And how about the estimates? There's still no effect from gender on reading test and from age on the reading test as well. So it's very obvious from these analyses that gender and age had no effect whatsoever on the reading test. In addition, there was no differential item functioning across gender groups for the 5 items. Alright, that brings me to the end of this video. I hope you enjoyed it, and if you liked it, please give it a like and subscribe to the channel. Have a great day. Goodbye.